Uh, Good evening, everyone. Today I'll be discussing whatever the course content is for the third week of the course and some of the old assignment questions. Um, so, okay. So, in week 2, we had briefly seen this. Uh, a sarcomere, which is the basic structure of any muscle. So between one Z disc to the next one lies one sarcomere. Okay, between one Z to the next one, and within this sarcomere there are these cytoskeletal elements known as myosin and actin. So the myosin that is present in the sarcomere constitutes the uh, heavy chain, constitutes the thick filaments of the sarcomere, whereas the actin marks the thin filaments. If you were to take a image of the sarcomere, the myosin is the myosin is connected to the Z disc via a protein called as titin, which basically acts as an anchor protein and keeps the myosin filament in place. Actin, on the other hand, is directly attached to the Z, and this alternating pattern is throughout the muscle, and whatever force is generated is eventually comes from this one sarcomere. There are other structural elements called M-line, H-band, which are basically used to denote how, what kind of structure a region of the sarcomere has. Okay. Please stop me if there are any doubts or any questions in between. Okay. Okay. So, so this is the basic structure of the sarcomere: alternating bands of thick and thin filaments. Thin filaments constitute of the of actin filaments, and thick filaments constitute of myosin filaments. So, so if you would zoom in into the sarcomere, you would see that the myosin has kind of a peculiar structure. It contains a head region and a tail region. So the tail region is the one which is called as the heavy chain, whereas the head region contains the light chain. The the tail region sort of wraps around with other myosin molecules and forms the filament, whereas the head region is the one which is involved in the force generation. Next, the thin filaments or the actin filaments are form another filamental structure with two other proteins, tropomyosin and troponin. Uh, so, uh, so there are two forms of actin that you would usually see within a cell. There is monomeric actin and there is filamentous actin. So the monomeric or globular actin is the individual actin molecules, whereas in case of a muscle, you would see when if you were to take a snap, you would see more of filamentous actin. So within the actin, within the thin filaments, there are tropomyosin and troponin molecules. What these two do is the myosin light chain or the myosin head has sites that would bind to the to certain sites in the actin filaments, which are known as actin sites or active sites, and eventually the binding of myosin to the actin filaments will lead to the power stroke. So what happens is that the troponin in a resting stage will arrange the tropomyosin such that it hides these active sites. In when there is a power stroke that needs power stroke needed, the troponin conformation changes, which is mainly owing to the calcium ions. Calcium ions will bind to troponin, and there is a conformational change which slightly moves the tropomyosin filaments that are wrapped around the actin filament, and the myosin head can then bind to the actin filament. So the whole process is called sliding filament theory, and so if you were to start from this particular point of the process, there is a energy unit that is utilized. So everyone knows ATP is the source of energy within a cell. So the myosin, the sarcomere sort of utilizes ATP. It breaks down ATP to release energy, and which then results in the force generation. So the myosin can only bind to the ATP binds to the myosin head here. Once the ATP has been hydrolyzed, and if there is so this is basically the preparation part, which you can see the previous step is the caulking of myosin head, wherein ATP is getting hydrolyzed and it is ready to bind to the actin filament. However, it won't bind unless it releases the inorganic phosphate or the Pi ion that is there present attached to the myosin head. Once the myosin head is just attached to ADP, the conformational change produced from this enables it to bind to the active sites on the actin filament, resulting in a sliding motion wherein actin gets pulled towards the middle of the sarcomere, which is the M line. Thereby there is a shortening of this entire sarcomere. So this happens, whatever you are seeing here happens in individual actomyosin level. However, because there is calcium released throughout the sarcomere, all of the myosin heads will interact with the actin filaments. Once the sliding the once actin gets pulled, the myosin is now in a low energy form. It has released the ADP. Now it can bind to a new ATP molecule, and this particular form is known as rigor. Then, because it's the binding site is free, ATP can bind to the myosin, and it is in ATP bound form. Myosin cannot bind to actin. There are certain conformational changes that occur that prevent the binding of myosin to actin. Following which, in the next power stroke, in the next release of calcium ions, the ATP gets broken down to PI and ADP, and then the process can repeat again. Cool. Okay, so we saw sarcomere, actomyosin, and sliding filament theory. So there are there is a certain length to the sarcomere. What that length is dictates what kind of force the sarcomere can generate. This is a dynamic process because there is no this is basically a dynamic process because depending on what kind of length the sarcomere is at, the force generation would vary. So the optimum conformation is such that there is enough overlap between actin and myosin actin filaments and myosin filaments such that they can bind to each other, and if maximum number of myosin heads can bind to the actin filaments, then the force generation would be more. However, the relationship decays on both sides. You see a parabolic nature of the curve, basically. If the sarcomere is pulled such that the overlap between the actin and myosin filaments is very low, then owing to the because there are not enough binding sites, the force produced will be less. So therefore it decays on this side of the graph. If there is too much overlap, the myosin heads are there, they are overlapping with the actin heads, but because there is so much overlap, the myosin can't bind to the actin filaments. So there is a decay on this side as well. But you can imagine a muscle as a spring of sorts, and the moment you start pulling the spring, you start feeling a resistance to the spring, and because of this there is a inherent passive force that the muscle generates once it's pulled or if it's contracted. And owing to the power stroke, there is an active force that the muscle is producing, resulting in a force that would be different from what you would expect from just a power stroke in the sarcomere. Okay. So next we'll discuss briefly the joints of upper limb and the muscles, and what the shoulder joint is, what are the muscles in that, and the movement of the shoulder joint. So the upper limb has, which is basically the whole arm plus the hand, has multiple joints. The main joints are shoulder joint, elbow joint, wrist joint, and finger joints. And the shoulder joint binds here, elbow joint is here, wrist joint is here, and finger joints are here. And depending upon what the joint type is, the movement will be different. So, and again, the muscles are also grouped into 4 groups. Muscles of the shoulder joint, which are near to the shoulder, anterior muscles of the forearm, or which is in the front of the body, posterior muscles of the forearm towards the back of the body, and muscles of the hand. Within the shoulder there are 4 major joints present. The sternoclavicular joint, which is basically here between the clavicle and sternum. It basically connects the upper limb to the axial skeleton or to the rib cage. This particular is a saddle joint, so 2 degrees of freedom. Next is the acromioclavicular joint or AC joint. It's the junction between the lateral clavicle and acromion process of the acromion process of the scapula, and this is a plane or gliding joint. Next is the scapulothoracic joint, which is basically it's not a joint, but it's not a true anatomic joint. It's basically a articulation between the posterior ribcage and the anterior scapula, basically in the back. But it does not move as normal joints do. Then there is the glenohumeral joint, which basically joins the humerus bone to the scapula. This is the joint that we'll be mostly focusing on, and it's a ball and socket joint, so it's highly movable. Okay, there are 5 major muscles that you would find in the shoulder region: the deltoid muscle, the subclavicus muscle, the trapezius muscle or the trapezoid, and the pectoralis major, and the sternocleidomastoid muscle, which is basically near the neck. Okay, all of these are slightly complex muscles. It might not have a single origin and a single insertion point. It might have multiple origins and a single insertion, or vice versa. For the deltoid muscle, the origin comes in 3 parts. There is the anterior border of anterior and superior surface of the lateral third clavicle, which is somewhere in the back here. There is the acromial lateral margin somewhere here, and the lower edge sits in the scapular spine. The insertion, however, is only 1 point, which is here, somewhere near the humerus. Okay, on the humerus. So this particular muscle can have flexion, adduction, medial rotation. It can also have extension, adduction, and lateral rotation of the combination of movements. Next is the trapezius muscle. It can bind here near the occipital bone. It can bind here, which is called ligamentum nuchae, or it can bind here between the T1 to T12 thorax processes of the spinal cord. Their insertion is also three-part. There is one insertion here, which is in the lateral clavicle. There is one here, medial border, and there is one here, which is to the deltoid tubercle. It can basically, this joint can rotate or elevate or retract the scapula. Next is the pectoralis muscle. This also has 4 different origins and 1 insertion point, but the major action that the joint produces is medial rotation and adduction of the shoulder joint, clavicular flexion or the flexion of the clavicle, sternocostal head extension to bring the flexed humerus to the side, basically flexion, and it's also an inspirator muscle, but we won't be looking at that here. Next, the subclavicus muscle, which is a very small muscle as compared to the others that we have seen. It basically holds the clavicle in the place. It steadies the clavicle. Then it's the muscles that are near the neck region or on the 2 sides of the neck. When they're acting alone, they can help in tilting the head in the ipsilateral shoulder or on the same side. It can act with other muscles in the neck region and sort of tilt the head forward or raise the head, or it can also help in thoracic elevation. Okay. The shoulder, the SC joint can basically lead to elevation and depression, or protraction and retraction of the shoulders as seen here. The AC joint, however, can lead to rotatory motion of the hand. So the major joint that we'll be focusing on, which is the glenohumeral joint, which is basically between the humerus and which basically joins the humerus to the body, and which is a ball and socket joint, can have flexion or extension, front or back movement, adduction, abduction and circumduction in the coronal plane, flexion and extension in the sagittal plane. Okay, now there are a couple of problems, but the solutions are not here, so I'll move to a different. So the problem is, a man is holding a 5.2 kg spear in his hand, with the arm held horizontally as shown in the figure. A tensile force in the deltoid muscle stops the arm from rotating about the shoulder O, which is here. This force is acting at a 21-degree angle. So whatever force is generated here. Determine the force exerted by the deltoid muscle on the upper arm at point B and the XY components of the shoulder joint. The mass of the upper arm is 2.1 kg, the mass of the lower arm is 1.5 kg, and the mass of the hand is 0.5 kg. And all of the weights have their center of mass in the points that is mentioned here. So I'll move. I have the solution here. Okay. So can everyone see this? Okay. Okay. So basically you need to find Fm, which is the force that is produced by the muscle, which is at a 21-degree angle. And these are the distances. This is basically where the muscle is producing the force. This is the center of mass for the upper arm, center of mass for lower arm, and the hand. So you can resolve the force into its respective fx and fy components, fmx or fmy components, and you can and you know the distance of each point from the origin. So the x component is, because it's acting in this direction, which is in the negative, it's minus fm cos 21, whereas the y component is f sin 21. And to find what fm is, you can write three different equations. The sum of all the moments is 0, the sum of all the forces is 0, and sum of all the in x direction and y direction is 0, because there is no acceleration of the object. So let's consider the moments equation. Sum of all the moments that is happening in the arm is 0. So there is one so the moments, sorry, one sec, the moments would come from the each of the weights that are, so basically the upper arm weight, the lower arm weight, and the hand weight, and the force that is generated by the muscle. However, if we are because there is no moment along the x direction, the x component of fm is 0. And so basically you write the equation fm sin 21 degrees into the distance 0.123 minus 2.1 into g 9.81 into 0.132. So write everything in SI units, otherwise you might get a number which has some extra zeros or some zeros less. Minus 1 point, these are minus and this was plus because this was acting in the upper direction. These are acting in minus y direction. Minus 1.5, 9.81 into 0.41 minus 5.7 into 9.81 into 0.64. Okay, and the x component 0. So you equate this, you find that the force is 1010.44 newtons. However, the there there is always the case that, so basically the force that needed to be balanced is 5.2, which roughly comes around 50 newtons, but the force that is produced by the muscle is this much. So the angle sort of plays a role. If the angle was 90-degree, then the force generated needs to be less. Okay, we'll also write the fx and fy equations. So there are reaction forces that are occurring at the origin to balance out all the forces that are happening here. So that there are two reaction forces, OX and OY. OX in the x direction, OY in the y direction. The x component is OX plus FMX, which is equal to 0. So OX is minus FMX, and FMX we had written here was minus FM cos 21. Minus minus cancels, FM cos 21. The answer is 943.33 Newton. Now the y component. So in y there are multiple forces. OY is the reaction force acting in the upper in the y axis. There is FM ka y component. There is the upper forearms weight, there is the lower forearms weight, and the hand plus ball ka weight. So this is the whole equation, and when you solve it you find that OY is 270.8 Newton. All of these are in positive direction. One second, excuse me. Are there any questions till now? Are there any questions till now? Okay. So we know all the forces that are acting in this problem. Now the next problem. So in the following figure, it shows an outstretched arm of length 0.61 meters or 610 mm in length that is parallel to the floor. So it's along the y-axis. You can imagine it's along the y-axis. The arm is pulling downward the pulley system in order to hold a 98 Newton weight in stationary. So whatever forces the arm is producing is basically balancing the weight of the of this 98 Newton weight. To pull the arm downward, the latissimus dorsi or the lats muscle applies M force, which is in this direction, at 0.069 meters from the origin or the axis of the shoulder joint, and the angle is 29 degrees. The arm has a weight of 47 newtons and the center of gravity is located 0.28 meters away from the axis. So find the magnitude of force M. Similar to the first question, I will open the solution. Okay. So remember two things. If the thing can't rotate, there is no moment component. If it can't accelerate, there are no reaction forces that exist. Or the moment component is balanced and the reaction forces are balanced. Okay. So this is the free body diagram of this problem. There are reaction forces at the origin, OX in this direction, OY in positive y-axis. There is the M force, or the force produced by the muscle, acting at 29 degrees to the hand, or the x-axis, in the negative y direction, and the weight of the hand is basically 47 newtons, the force that the hand feels because of the weight of the hand, and there is a 98 newton force that is being balanced because of the pulley. So same three equations, fx is equal to summation of fx is equal to 0, summation of fy is equal to 0, and summation of the moments is equal to 0. Now the m again can be divided into its fx and fy components. The fx components, since it's in negative x direction, is minus m cos 29 degrees. The fy component is in a negative y direction is minus m sin 29 degrees. And the moments of around the origin, or the point O, or the axis of the shoulder joint, is 0. So you solve the moments equation, minus fm sin 29 degrees, which is comes from the y component of the force, into the distance, which is 0.069, minus 47 into the distance 0.28, and plus 98 into 0.61, which is the distance from the axis of the pulley, and fm comes to about, you solve this equation and fm comes to about 1393 newtons. The reaction forces then, summation of fx is equal to 0. In the x-axis you only have the reaction force and the x component of the force m, which is minus m cos 29 degrees. So OX is minus FMY, or FY, FX, sorry, FX. OX is minus FX, which is basically m cos 29, which comes around to, not so much, it's, I think one of the ones is extra, it's 1218 newtons. Now summation of Fy is also equal to 0. In the y there are four things that you need to consider. The reaction force, the y component of the reaction force, or Oy, the y component of m, which is Fy, which is minus m sin 29 degrees. Oy is what we would like to compute, and the weight of the arm itself 47 newtons, and the resistance by the arm to maintain the pulley at its point, which is 98 newtons. So OI is equal to minus f sin 29 degrees minus 47, because 47 is in the downward direction, plus 98 because it's in the upward direction, is equal to 0. So OI comes out to be 624.65 newtons. Okay. Okay. Uh, so the elbow joint is has three major bones that comes into play in the elbow joint. Uh, the humerus, or the bone of the upper forearm, the radius, and the ulnar bone, which in the lower forearm. And the elbow joint, when you talk about elbow joint, it's basically an hinge joint. It acts like a hinge. So there are three joints. So a joint would be between two bones. So because there are three bones, there are three joints. The joint between the radius and the humerus, which is the radiohumeral joint. The joint between the ulnar bone and the humerus, which is the ulnar-humeral or humero-ulnar joint. Sorry. The joint between the radius and the humerus, which is the proximal radio-ulnar joint, which is here. There is a distal one near the hand. Okay. The elbow joint is not, the muscles of the elbow joint are not confined to the elbow joint itself. It has muscles inserted from the shoulders and till the movement of the elbow is involves muscles which have the origin starting from maybe the shoulder to going on maybe till the lower arm or near the hand. Not necessarily the same muscle, but you get the point. So there are upper arm muscles and there are lower arm muscles which come into play when you are talking about the elbow joint. The first one is biceps brachii, or biceps as we say. So again, these can, there is a short head and a long head, basically two muscles, and both have different origins and insertions, but the actions that they perform are supination, flexion of the elbow joint, and the long head is responsible for keeping the humerus in the glenoid cavity during the abduction of the shoulder joint. Okay. Next, the brachialis, or which again has multiple origins and insertion, but the action that it's responsible for is the flexion of the elbow joint. Okay. Next is the triceps, which is towards the posterior of the, so or these muscles that you saw is on the anterior side of the forearm. The triceps comes in the posterior surface. Again, there is a lateral head and a long head, and a medial head, and all of these have different origin point uh, and insertion points. However, they have a common function, which is the extension of the elbow joint. Okay. Next is the brachioradialis, coming to the lower forearm. The brachioradialis, the lower forearm has more major muscles. The major muscles in the upper forearm were restricted to the triceps brachii. The brachioradialis has the major action that it is responsible for is the flexion of the elbow joint. Then there is flexor capi radialis, uh, which is basically the insertion is in the metacarpal bones, which is in the palm region. And the action that it is responsible for is the flexion of the wrist, not the elbow joint, the flexion of the wrist. Again, flexor capi ulnaris, it's the origin is in the ulnar bone. However, it binds to the metacarpal bones. It inserts into the metacarpal bones. It also has the action of flexion of the wrist and adduction at the wrist joint, or the radial deviation. Next is the flexor digitorum, or uh, it it basically has it inserts into four tendons and it splits, but the main action that this muscle is responsible for is the flexion of the middle phalanx at the proximal interphalangeal joint, basically flexion of the fingers. Okay, so we saw flexion and elbow joint is responsible for flexion extension, and it seems like elbow joints are responsible for pronation and supination, but the elbow joint in itself is not responsible for it. The by elbow joint I mean the ulnohumeral joint, which is the joint we talk about when we talk about elbow joints. But it's the joint between the ulnar bone and the radius that is, or the radio-ulnar joints that are responsible for pronation and supination. Okay. We'll look into another static problem. So a person pushes down on a load cell with the palm of his hand as shown in the figure. The reading of the load cell is 150 newtons. Determine the vertical force F generated by the triceps muscle. The mass of the lower arm is 1.5 kg with a mass center at G. This is the G. So this is the origin. This is where the muscle is inserted and the force produced. We need to find the angle of the force first before moving on to the solution of the problem. Is there a question? Okay. Just okay. So this is the free body diagram of the problem. So the origin is here, the muscle is inserted here, the distance is 25 millimeters. The center of mass for the arm itself is somewhere around here, and it basically experiences a force of 1.5 kg. The reading at the load cell is 150 newtons, so it's the reaction from the load cell is happening in the upper direction, so 150 newtons here. Again, same, summation of m is equal to 0, summation of fx is equal to 0, and summation of fy is equal to 0. Summation of m is equal to 0. So there is, in this So first you need to okay. I don't have this written here, but you need to find the the angle of the force. Just a minute. Before you can resolve the problem into the fx and fy components, you need to find the angle of the force. Have no, sorry, that's the next problem. Sorry, never mind. So it's the force is acting in the upper direction, uh, because it's acting here. So you write the moments equation. Fm into 0.025 is 0.025 minus uh, 1.5 into G 9.81 into uh, 0.15 and 150 into, so sorry, this should be in the downward direction. Anyways, uh, and you solve this, you find that Fm is 1711.71. Sorry for the confusion. This is the next problem, which is here. A person is performing slow arm curls with a 10 kg weight as shown in the figure. The brachialis muscle group, biceps and brachialis muscle, is the major factor in this exercise. The dimensions are given in the figure. Include the effect of 1.5 kg forearm mass with the mass center at point G, which is here. Determine the magnitude F of the muscle group and the reaction force at point E for the forearm as shown in the figure. So we don't have the angle of the force here. Here it was perpendicular. However, here it is not. To calculate the angle of the force, we can consider the origin to the insertion point, which is 200 millimeters or 0.2 meters, and 0.05 meters is the length of the insertion from the origin or the elbow joint. And you solve it, you find that you basically apply Pythagoras theorem. Tan theta is equal to, you basically look at the tangential factor, and you see that theta comes out to be around 76 degrees. Okay, theta comes out to be around 75.96 degrees. And so there are three things that there are reaction forces, which can be split in x component and the y component. There is the force that the muscle produces, which can also be split in the x component and the y component. The weight of the arm itself, which is 1.5 into 9.81, and the weight of the ball or weight of the barbell, which is 10 into 9.81. the moments equation equates to 0. There is no acceleration, moments are stabilized. So all of these two are in the downward direction. So negative 1.5 into 9.81 into 0.15 minus, again in downward direction, 10 into 9.81 into 0.35 plus the force produced by the muscle has a positive y component. So plus Fm sine 75.96 degrees into 0.05 is equal to 0, and Fm comes out to be 753 newtons. Again, the reaction forces are balanced. So summation of Fx, there is no acceleration of the system itself. The summation of Fx is equal to 0. Reaction forces at the origin plus Fx component of Fm is equal to 0. So Rx minus Fm cos theta, because it's the x component is in this direction, is equal to 0, and Rx comes to be 182.76. Again, the y component, the reaction force by the reaction forces in the y direction, Fmy or y component of Fm, and the downward two weights. You solve this and you get the reaction forces to be 618.03 newtons. Are there any questions till now? Are there any doubts or questions till now? If not, I'll move to some of the old assignment questions. I'll try to have some numerical problems next time. I don't have them on me right now, but I'll have them next time so we can practice some of them together. And if there are any questions, guys can ask. Okay. Okay. These are the old assignment questions, not from the current assignment. The thick filament, it is attached to the Z disc by which of these four? Troponin, ryanodine receptor, titin, and tropomyosin. So if you were to if you were to see this, the thick filaments or the myosin filaments are attached to the Z disc by titin. So the answer is titin. The pulling force by myosin heads following hydrolysis of ATP is known as cocking, rigor, sliding, or power stroke. Which is basic. Is there a question? Yeah. The answer is D, power stroke. Okay, sorry. The answer is power stroke. Next, in presence of calcium, troponin undergoes a conformational change, moving tropomyosin, exposing actin binding sites. It undergoes a conformational change, moving troponin. Tropomyosin undergoes a conformational change, moving troponin, exposing myosin heads. Or troponin undergoes conformational change, moving tropomyosin, exposing myosin heads. Or fourth option, tropomyosin undergoes a conformational change, moving troponin, exposing actin binding sites. Anyone wants to hazard a guess for this question? Okay. Um, the answer is A. Troponin undergoes a conformational change, moving tropomyosin, which expose the actin binding sites in presence of calcium. The conformational change, however, happens in troponin, not in tropomyosin. Force produced in a muscle fiber depends on number of sarcomeres in series in a microfibril, both average force of its sarcomeres and the number of sarcomeres, average sarcomere force, or the number of sarcomeres in parallel. The answer is number of sarcomeres in parallel. They add up in series to give the force that is generated within the muscle fiber. And at optimum sarcomere lengths, the force is maximum because A, there is no overlap between thick and thin filaments. B, there is an overlap between thin filaments. C, there is just enough overlap for forming maximum cross bridges. Or D, there is too much overlap such that thick filaments touch the Z disc. If you were to see this, you'll see that there is enough overlap between the myosin and actin filaments, so that all of the myosin filaments have their corresponding actin partner of sorts, and so they can bind. So the answer is there's just enough overlap forming maximum cross bridges. The bond that forms between a myosin head and the actin filament is called a cross bridge, if I haven't mentioned that. Okay. At low sarcomere lengths, the force produced is low because A, there is no overlap between thick and thin filaments. There is overlap between thin filaments, reducing the area available for cross bridges with myosin. There is just enough overlap, but there is no calcium. There is too much overlap such that the thick filaments touch the Z disc. Again, coming to this, at the short sarcomere lengths, which is here, the actin fibrils overlap each other, masking the sites that the myosin would bind to. So the answer is B. There is an overlap between thin filaments, reducing the area available for cross bridge with myosin. Which protein is responsible for storage of large amounts of calcium in sarcoplasmic reticulum? Titin, calsequestrin, ryanodine receptor, tropomyosin. Remember, titin is the protein that is responsible for myosin stabilization. Ryanodine receptor is the protein that is responsible for within the sarcoplasm to control the calcium flux. It acts with DHPR receptor. Tropomyosin is responsible for masking the active sites. Calsequestrin is the molecule which is responsible for storage of calcium. It can store up to somewhere between 10 to 50 calcium ions. One protein can store that many calcium ions. Basically, it will bind, and calsequestrin is localized to the sarcoplasmic reticulum. Therefore, the answer is calsequestrin. Action potential at muscle fiber is triggered by the influx of sodium ions through A. Acetylcholine gated sodium channel, B. Voltage gated sodium channel, C. GABA gated sodium channel, or D. Calcium channel. Remember, at the neuromuscular junction, there is release of the neurotransmitter or acetylcholine into the synapse between the into the neuromuscular junction from the synapse, and this acetylcholine binds to certain channels on the sarcoplasm, on the mus- on the membrane, plasma membrane, which are responsive to the acetylcholine that is getting secreted. So the answer is acetylcholine gated sodium channel. So depending on what is the ligand for a particular channel, if it's a, remember, a channel will, in case of a channel, something will bind to the channel which will cause a conformational change, which will allow for influx or outflux depending upon the gradient. Whereas in case of a pump, and similarly in case of calcium channels that are present in the sarcoplasmic reticulum, there is always outflow of calcium ions from the sarcoplasmic reticulum into the sarcoplasm, never the other way. The other way is done by a pump, which is going to go against the gradient. Pumps always mostly go against the gradient, and they need to employ energy currency or ATP to do this. Okay, just keep this in mind. Okay, arrange the following events in order of their occurrence during excitation contraction coupling. Release of calcium ions from the sarcoplasmic reticulum, activation of dihydropyridine receptors or DHPRs and ryanodine receptors, action potential propagation along the sarcolemma. And so basically, once there is neurotransmitter released, there is an influx of sodium ions inside the uh, plasma membrane. This influx of sodium ions causes depolarization, which generates the action potential along the sarcolemma, which then the action potential reaches the T tubules, then activates the DHPRs and the RYR receptors, and this in turn triggers the release of calcium ions from the sarcoplasmic reticulum. So the correct answer is 3, 2 and 1. What is the I band in a sarcomere mainly composed of? So if we come here, okay, so this is the I band. Okay, it has Z disc, it has actin filaments. Okay, sorry, uh, it has actin filaments, it not M light. Sorry for the confusion. Are there any questions in the presentation or in the old assignment questions? or any of the previous week's questions. Does anyone have any doubts? Yes. The recap of the lectures and the questions are over. I'll try to have some numericals next time so that you get some more questions also. But if there are any questions in this week's um lectures or the previous weeks, please let me know. Otherwise, it's over. Uh, Thank you. I'll just hang around for a bit. If there are any questions, you guys can ask me. Okay, that will be all for today. Thank you, everyone. I will sign out.